Hello, this is Megan Dodson. I work with the National Weather Service in Northern Indiana, and this is the Lifeguard training for 2018 for taking weather observations for our office. So just to give an overview of what we'll talk about today, we're going to give a little bit of an introduction to the National Weather Service and the program overall and the project that you're taking observations for. We're going to talk about waves and currents, get the basic 101 of how these things work and what they have to do with your job. And then we're going to talk about taking observations, such as looking at the forms that you'll use and talking about, what kind of things you're going to actually observe and how to observe them. And then we'll talk about some severe weather 101 and a little bit of resources that you can use. For those of you that were involved with lifeguard training last few years, way to go. It looks like from the modelers at the National Center for Environmental Prediction, they said that the observations have been good quality, so keep doing what you're doing and pass the knowledge on to the new folks that are coming in. So who is the National Weather Service? National Weather Service mission is protection of life and property and enhancement of the national economy. And that's what we do our forecasts and warnings for, and provide decision support services. Our vision is that we have a weather-ready nation. This means we want people in the society to be ready, responsive, and resilient to the impacts of extreme weather and water events. We always say the Beach Hazards mission is a water-ready nation, which is society prepared to swim in the Great Lakes. So that means, from the Weather Service aspect, we want to make sure that our partners, such as you, the lifeguards, have the forecast data and support you need to make water safety decisions. So we produce forecasts, we produce warnings, we do education and outreach, we do research such as this project, and collaborative efforts such as this project as well, and decision support services. So if you're not familiar with the National Weather Service, there's 122 offices all the way from Guam and Alaska over to the Great Lakes region. Our office is shown by the pink star. This is the National Weather Service in Northern Indiana, or IWX. So IWX, if you're not familiar with Kosciuszko County, is basically in the cornfields out in the middle of nowhere near North Webster. And so we're about an hour and a half from the beach. This is our forecast area. That means the place that we actually do our forecast for and the counties that we are including in our forecast area. And, one of the things I always like to talk about is why do we care about waves and currents so much as the Weather Service? You think that our main focus would be things like severe weather and tornadoes, especially given that our forecast area only has two counties on the lakeshore, Berrien County, Michigan, and LaPorte County, Indiana. But if you look at this, for all the counties shown in the white, from 1980 to 2017, these are the numbers of deaths we've had from floods, lightning, winds, which includes thunderstorm and non-thunderstorm winds, and tornadoes and hail. You can see the numbers are pretty low. We have 14 deaths from flood, 13 from lightning, 9 from winds, and about 7 from tornado. To our knowledge, we've had 0 deaths from hail. But since 2000, not 1980, we've had 29 fatalities due to waves and currents. Those two counties only in that blue area. So you can see the dramatic difference not only from the time span that it covers, but the number is way above the others. So this is why we care at our office and why we have a marine program. Because even though our marine area is really small, we see a lot of fatalities and a lot of rescues from waves and currents. So if you look at the whole Great Lake, this is a map of the number of current-related incidents, which includes rescues and drownings, fatalities, on the Great Lakes since 2002. And you can see that Lake Michigan is definitely above the rest. Now this is partially because some of the data that we collect isn't as quality of data in Canada, just because it's harder to get a hold of the information we need to confirm incidents. So that is one thing to keep in mind. But Lake Michigan still stands above the rest by far. If you look at the current related incidents by lake, that Lake Michigan has 392 incidents total, whereas Erie, Superior, Ontario, and Huron aren't even into the triple digits yet. So since 2002, our entire database includes 552 incidents, and this is as of June 1st, 2018. So what are the victims like that usually get caught in these currents? Most of them are male. About 69% are male and about 31% are female. And this is generally because males tend to take more risks than females. The age between 10 and 21 years old, again, that's just because usually adolescent age or young adults have a lower capacity to understand risk, and so we see problems with that. And there's a lot of peer pressure going on when their friends are there. Interestingly, we have most of the people that get into the trouble living within 90 miles of the beach. And actually, quite a high number of them live within 10 miles of the beach that they either were rescued or drowned at. So it's not just a tourism thing, it's also a local, but we do have a fair number of tourists that come in as well. So what is the purpose of the lifeguarding project? Ultimately, it's saving lives. With your lifeguard awareness and knowledge, your observations and your understanding, plus our forecasts and statements, will help to increase public awareness and save lives. The lifeguard observations feed into the model, which helps improve our forecasts. It helps NOAA researchers, and it adds credibility to the forecast. When you submit your observation, we send it out in the morning statement that we send out to the media and to our partners and to the public that says this is what the flag color is, this is what the water temperature is, this is what the waves and the currents are like. So you're helping to raise awareness and verify things. So if we have a high swim risk and then your report comes in with, rip currents observed or high waves, then that validates the forecast and adds credibility. And we've learned from sociologists that leads to a greater public action. They're more likely to take action once the conditions we forecast are verified and they can actually hear that somewhere familiar to them, like Silver Beach, is seeing those conditions. So we want to increase public awareness and ultimately save lives. So as far as lifeguard awareness and knowledge, the things that you need to know are where, when, and why dangerous currents form. You need to use the correct terminology because sociologists have taught us that people need to hear the message consistently using the same terminology from a number of sources, as many as possible, before they really truly understand it. And the more they hear it and the more it's consistent, the better they're going to understand and remember it. You need to know how to get forecasts and statements. You need to know how to submit accurate observations of currents and wave to the Weather Service. And knowing when lightning and severe weather are possible is obviously important to get people to safety in time. So if you haven't seen the beach forecasts and statements from the National Weather Service, our slogan is know before you go. And we say know before you go into the water and before you even go to the beach. So we encourage people to check the swim risk. The swim risk is the potential for hazardous conditions to swimmers. So for example, when we have a high risk, which is usually 3 to 5 foot waves, and dangerous currents present, we say to the public that there are life-threatening waves and currents expected and to stay out of the water and stay away from the piers and breakwalls, which we'll learn about in a little bit. And when it's more moderate risk conditions, that's the 2 to 3 foot waves, 2 to 4 foot waves, we just say breaking waves and currents are expected, and then we still encourage people to stay away from those dangerous areas like breakwalls and river mouths, and to have a flotation device if allowed in the water. When we have low risk conditions, it doesn't mean no risk, but we say that dangerous currents can exist near piers, breakwalls, and river outlets, so we don't want people to swim there, even though the likelihood that they'll encounter one of those currents outside of those situations is pretty low. And that's usually when you have about 0 to 1 to 2 foot waves. And in our database, it shows that 86% of our incidents occur with high swim risk conditions, which is why we assigned a high risk to those conditions. And that's those 3 to 5 foot waves where people are likely to go in the water because they're not too big of waves to intimidate them, but also that those conditions are present and dangerous. But once you get into those lower risks, you'll notice there's a little bit of overlap between the wave heights, like a low to moderate risk, 2 feet and between 3 and 4 feet. We have about 15% of our incidents on slightly lower confidence, but this is because we are not as good at forecasting these lower risk conditions, so moderate risk particularly. Obviously, when it's really low wave heights, we have a better handle on things, but when we get to the moderate risk conditions, when you get to that 3 foot wave height, approximately 3 feet or so, we've had incidents where there have been stronger rip currents or stronger currents near the break wall. So these are those kind of conditions that your observations are really going to help us nail down as we get this model that's calibrated from the ocean to the Great Lake. And that's what we're really looking to aim to improve as far as our forecasts go. So keep that in mind when you look at the forecast on our webpage. Speaking of the webpage, this is what it looks like. It's weather.gov/Great Lakes/beach hazards. On our webpage, you can zoom in, but this is the Great Lake. You'll see each shoreline is colored by either red, green, or yellow, depending on what the swim risk is. So for this example, you can see in Berrien County and LaPorte County, we have a high swim risk. And you'll notice that the counties are colored teal wherever there's a high swim risk. And this is because we have a beach hazard statement in effect. So whenever we have that high swim risk out, we put out a statement that highlights the web page and draws extra attention to that area. So when the public comes, they're more drawn to click on it. This is an example of a beach hazard statement, and we basically give a little bit more detail on what is expected. So we say, strong rip currents expected, strong structural currents expected, what the winds are going to be like, the area, and the terminology. So now we're going to go a little bit more into waves and currents. And it's important for you to understand how things are working in the water so that you can answer questions that people may have, or you can guide people to the safer areas. So how do currents form? Currents form when water piles up near the beach. And that's the really non-scientific example, but it essentially is true, is that when that water accumulates near the beach, it has to go out somewhere. And so usually it will go out in the form of a rip current, which you can actually see from the muddy water here, where the water's coming up, piling up near the beach, and then moving out in between gaps in the sandbars. You could tell that there's a current there from that muddy look to the water, or sandy look, and then also you can see the break in the waves. There's one break, here's a wave, and then there's a break where that water's moving out. And those are typical signs. So what causes water to pile up near the beach? Beach features like a gentle slope, sandbars, shoreline structures like breakwalls or piers, and river outlets. As far as water conditions or wind conditions that cause it, when you get strong onshore winds, it builds up the waves. And if it's a more direct approach, like the waves are coming at a 90-degree angle to shore, you're more likely to see that water pile up. Wave period, or the time in between waves, and water level fluctuations also can cause currents to develop. And we'll go over each of these in detail. So where do currents form? So we know structures like piers and breakwalls, river outlets, and in between the sandbars. And we know we have all three of these features in the Great Lakes. So here's the Great Lakes Surf Rescue Project's diagram that encompasses most of the current types on the Great Lakes. So we have currents and waves that interact, and they can cause a swimmer problem. So when the winds and waves come in, and say they're about 2 to 3 feet, and you have in this case, a 45-degree angle of approach, you start to see the water moving towards the beach, and that piles things up. So first, what'll happen is a longshore current develops. And that's where you go into the water and you kind of notice that you're being pushed along the shore. And this current isn't really dangerous in itself for adults. Usually it's intuitive to swim back to the beach to get out of it, but it does contribute to other incidents. So by itself, it's only cause of about 1% of the incidents. However, it does sometimes cause people to drift out on rafts and things, and it also strengthens other currents. So this, though it's not really a danger in itself beyond, maybe smaller kids, is in the trough of the sandbars, it can contribute to those other incidents. So once that longshore current flows down the beach and hits a pier or some kind of structure like this, and it could be a peninsula, it doesn't have to be an actual pier, and this accounts for about 49% of the incidents or drownings or rescues in our database. So as it intersects the pier, it moves out. So if anyone who's jumping off of that breakwall or pier are going to be jumping right into that current. And this is what we call a structural current. Swimming out of this current is nearly impossible. As you try to swim this way or towards the left in this image, you're going to be going into the longshore current, so you're not going to be able to really make much progress. Try to swim back to shore, you're going to be stuck there as well because there's an outward flowing current that can be very strong. And you combine that with the wave action that's usually near the pier. As it bounces off, the waves bounce off. So this is why we tell people steer clear of the pier, because your traditional escape methods, currents, which usually we tell people swim parallel to shore, is not going to work in this case. Channel currents are a little bit different. If you have a situation instead where the longshore current's going and you have maybe a offshore island or some rocks usually, and then there's a sandbar that kind of connects those, and it gets a little bit deeper towards the channel. As that water gets squeezed between the rocks and the shoreline, it's almost like putting a smaller nozzle on a hose. It's going to increase in speed. In addition, it goes up and over that sandbar, so it's being squeezed horizontally and vertically. So this can cause the water to enhance itself once you get closer to those rocks or that island. So this pushes people off the sandbar, and then they try to swim back towards the sandbar and they end up drowning. So they exhaust themselves by trying to fight that current. So if you have a stronger longshore current, the risk of the channel currents is going to be a lot higher, and a stronger structural current as well. And the channel currents account for about 3% of the incidents. Rip currents are about 39% of our incidents. These occur within the gaps of the sandbars along the beach, but this is about 39% of our incidents. If it's a direct approach versus this is a more of a 45-degree angle, if it was coming directly on the beach, this would be a lot stronger. So depending on the angle of approach will determine what kind of strength and the number of rip currents that you see on the beach. We also have outlet currents. Outlet currents are simply a water outlet. So this could be a mouth of a river or a little stream. But what happens is this little area here acts sort of like a rip current channel. And when you get more direct wave approaches, that can kind of enhance, this acts like a little break in the sandbar, and combined with the outflow of the water, which sort of pushes people out anyway, this can be enhanced and be a little bit faster than normal. And a lot of this, we have about 8% of our incidents that occur near the mouths of rivers or similar outlets, near power plants and things, because usually people like to swim near the river mouths because the water's a little bit warmer. So we try to raise awareness. We sort of say forget the outlet because it can be suddenly enhanced maybe overnight due to heavy rain. The water outflows a little stronger than normal and pulls people out. So here's a chance for you to apply it. I'll read the question and then you can think about the answer, and then I'll give you a few seconds and we'll go on. So what type of currents are possible at Silver Beach? What about at Tiscornia Park? And why? Okay, well, I gave you a couple seconds there. Hopefully you said that longshore currents are possible. You can see we have those sandbars there, so rip currents are possible. Especially here, you can actually see where the water was moving out. There's a dark spot. This is a Google satellite image, so you can see these are the sandbars here. But you can actually almost see the shape of the rip current there as that water moved out, and then here again as well. And then along the break wall, you can also have structural currents. So both of these can have longshore currents, rip currents, and structural currents. We don't see any offshore islands or anything, so channel currents wouldn't really be an answer. And we don't have any outlets, so that wouldn't be included here either. How about at New Buffalo? I'll give you a few seconds to answer. Okay, it looks like we have a structure here, so it's a pier break wall. We have sandbars, so we have a longshore currents possible, and we have a giant gap in the sandbar here that could be from a past current that would be outward flowing, or it could just be a deeper spot. It's hard to tell from this image. But you can definitely see there's a channel carved out right here near the break wall, and that's where that outward flowing structural current goes. So structural currents, longshore rip currents are definitely all possible at this beach. Quiz question number 2. A swimmer at this beach wants to know why she keeps drifting north towards the pier. She gets in the water where the blue star is at this moment. How would you explain this to her? A, she's caught in a rip current. B, she's in a structural current. C, tell her she's imagining it. Or D, longshore current. So you see she's moving along the beach. And the wave direction in this case is at about a 45-degree angle. So that water's coming in, and the yellow lines depict where she's kind of headed. The correct answer is D. She's caught in a longshore current. And if she continues to go towards this area, she may eventually get caught in that outward flowing structural current. So here's quiz question number 3. What kind of currents are possible here? It doesn't look like there's any structures, so structural currents would be out. I don't see any river outlets or anything like that, or offshore islands that would make a channel current or an outlet current possible. So it looks like rip currents are possible here. We definitely see sand, so there's probably sandbars underneath the water. And if you look actually very closely, you almost wonder if there's something going on right here with some kind of rip current. As you can see, there's a little break in the waves, and the water looks a little choppy there. Similarly here, we can sort of see the water going out, and there's a little bit of discoloration. So the answer would be rip currents, and of course, as along any shoreline, the longshore current is possible. So what kind of conditions cause currents to develop? We talked about this a little bit already, as I've mentioned the wave height, the wave period, and the angle of approach of the waves relative to the shore. So those are the 3 main ingredients. You can also have water level fluctuations, which we haven't really covered yet, but we will in a little bit. So this is a general synopsis. The higher the waves get, the stronger the currents are going to be and the more organized they're going to be. Especially if you have the higher waves, what usually you'll see is with the lower waves, like 2 to 4 feet, 2 to 3 feet, you start seeing weaker but more numerous currents. But as you get to have higher waves, especially with more direct approaches, the system of smaller currents isn't efficient enough to move the water offshore. So what ends up happening is you get less currents, but they're stronger. So you get more focused energy. So wave height, as the wave height increases, especially above 3 feet, you start to see an increasing risk of currents. With the wave angle of approach, if you get a more direct approach, such as a 45-degree to 90-degree angle, you're going to see a greater likelihood of currents, especially when it comes to rip currents and outlet currents. Wave period is the time in between the waves. So you can see by the little bar there. So if you get hit by a wave, and then about 5 seconds later, another wave hits you, that means the wave period is about 5 seconds. So it's that passing time in between waves. So once you get to about 5 seconds, you get a larger volume of water coming to the shore. So that causes the water to increase, or the water to pile up, like we talked about. So that means you're going to get those stronger currents. So if you have like maybe a higher wave height, and then you have a more direct approach and a longer wave period, you're going to have a perfect recipe for really strong currents. So wave height. So as we said, we'll go over these individually. As you get higher waves, the risk of dangerous currents increases. High waves in themselves are alone a hazard even without strong currents. So what the Weather Service does is when the waves get 3 feet or greater, usually when we start seeing the 3 to 5 foot category, we say that, even if there was no rip currents developing, which there usually would be at this, at those wave heights, even if there wasn't, the waves alone are a hazard for swimmers, just because often the wave period on the Great Lakes is 3 to 4 seconds, so they don't have a lot of time to recover if they're knocked down. And you can actually see this in the data with all of our incidents. We have about 185 that happen in 5 to 6 foot waves, but notice that as you get above that, the incidents actually drop off quite a bit. And that's because most people aren't going to go swimming in 7 to 8 foot waves or higher. It's usually very intimidating and people don't feel safe, so they will stop. But when you get those 3 to 6 foot waves, you start to see probably, the more adventurous type go into the water, and they're also feeling like it's not a big deal, I could handle it. So that's why you see that big increase right between 3 to 5 and 3 to 6 feet. I also noticed that there was quite a bit, about 71 incidents that happened when the waves were like pretty much calm or 1 to 2 feet, and that's really unusual. So what was the case with that? We'll go over that in a second. But one of the things I wanted to point out was, the safety message: stay dry when waves are high. This is why we say that. It's because that current and wave combination is deadly. So those incidents where the wave heights were 2 feet or less, a majority of those were, about 73%, were either near a structure, such as a pier or breakwall, a river outlet or stream, or a channel current. So this is why we say dangerous currents are still present near river outlets and structures, even when the waves are pretty calm. It depends on the person's swimming ability as well, what they're going to be able to deal with, and whether they panic, and if they know how to escape, what's going to happen. But looking at just strictly the rescues and fatalities, about 73% of those lower wave height incidents happen near those features. So we try to keep people away from them regardless of the conditions. On the other hand, we have longshore currents that account for about 7% of these incidents. The other ones, about 10%, were actually rip currents. And those were cases where usually the winds were coming down and the waves were coming down. So those decreasing waves, and the conditions were just enough, maybe longer wave period or a direct approach, that there was still momentum going with those currents. So we usually tell people, even after the wave heights diminish, that doesn't mean the currents stop right away. You're going to want to make sure, maybe just keep people out of the water just a little bit longer after those conditions subside, just because of that potential. But it will depend on what you're seeing in your observations. So talking about current conducive conditions, we'll talk about this wave angle, and it always helps to have a visual. So when you have a more 90-degree approach, so that means the waves are coming directly onshore, you get strong rip currents and a strong structural current. This is because this is when the piling up of the water is maximized. In addition, the Great Lakes, these sandbars act to pile the water up even more. So you have that feature here, and you have the breakwall, which also acts to pile the water up. If you have an outlet like this, you're going to also see water pile up. So you have this ideal condition. So what's going to happen is when you get that, if you have a decent wave heights and decent wave periods, you're going to have strong rip currents, strong structural currents, and weak or non-existent longshore current. This is because the water is just coming right back offshore. It's not going to be traveling along the beach like we'll see in a minute. So this means that you can get these stronger currents, you get a greater variety of currents, and if you have higher waves, this is like the perfect storm. Now, if the waves approach at more of a 45-degree angle, so it could be from the southwest or from the north, you get a stronger longshore current. That 45-degree angle is sort of the sweet spot for longshore currents. So when you get that longshore current, which is shown in red here, it really starts moving along the beach. You're going to get rip currents, which are shown in yellow, forming in the sandbars and the gaps, though they will be at an angle, whereas the last example, they were straight out. They might be more angular, and they might actually kind of get absorbed a little bit in that longshore current, depending on how strong it is. Usually the speed is pretty moderate to strong, and they'll probably kind of move more with that longshore current. Once that longshore current hits the breakwall, it's going to move out into the lake as a structural current, and that means you're going to have strong structural currents expected, and that's what we really see with our data. As far as the 0 to 30 degree angles to shore, those little bit closer to the shore or shore parallel winds and waves, you start to see this weak or moderate longshore current, which means you could have a moderate structural current, and you get weak flow in the rip current. So in these cases, a lot of times the water is just moving parallel to the beach. They're possible to have rip currents, but it's not really likely just because that water's not being piled up as efficiently due to the angle of the waves coming in. So you might have some weaker rip currents, which would be dangerous to swimmers, but it's unlikely. The biggest threat in these types of environments, and we've had a lot of incidents in these environments because of the sandbars that kind of make that enhanced a little more than it would normally be, and also because people are jumping off the breakwall into the water and right into that structural current. So that's where we've had most of the incidents be about 0 to 30 degree angle are from structural currents. So here's an example from Port Washington. And this is done by Chin Wu and his graduate students in Wisconsin, and the website's there on the left. And this is a really cool website to watch when you're in the summer, maybe on a day with northeast winds or southeast winds, because you can actually see this real time. There's a camera that actually measures the currents on the water. So they have a camera that visualizes it, and then they kind of put the flow on their website. Now you can actually see where in this case the winds were southwest, so the water's flowing here along the beach and then out along these structures. It's enhanced, kind of comes around, and it actually does a little spin and goes as the waves kind of get refracted around, it kind of regurgitates back on the back side. And so even if there's southwest winds, you would think maybe this side might be safe, but there's still some currents there. And this is actually a really cool example. They showed the velocity of that current, and this is neat. It actually shows the current day with the east-northeast flow, and you could see the water just piling up and coming along the shore. There's that longshore current, and you see how far it extends out. And the longer the arrow, the more strengthened it is, and not my arrows, but the arrows that are black there. But you can see it really gets focused around here and kind of comes back. So this is a place you definitely don't want to be, but it's neat because you can actually see this real time. So quiz question number 4. What wind and wave directions will be hazardous at Silver Beach, A, and New Buffalo, B? Silver Beach is on the left and New Buffalo is on the right. At Silver Beach, which is on the south side of the breakwall, you have the sandbars. We talked about how longshore currents, structural currents, and rip currents are possible. On these days, southwest winds, west winds, northwest winds even, would be favorable for current development. Now, so southwest and west. Now, if you get a northwest and northwest wind, you're going to see problems more at Tuscarora Park up on the north side. As far as New Buffalo, if they're swimming on the north side there, you have potential for a longshore current to develop, and that would be with a northerly winds. So northwest, northwest, and even northeast, as the beach kind of, this would be northeast flow like this. So the north is just up here. So it's a little bit of an angle. Quiz question number 5. What type of current do you expect with this wave direction, height, and period? So this is, we'll talk about at Silver Beach, not up at the north side, so we'll be on the south side. So let's say our wave angle relative to shore is west-southwest, so it's about a 60-degree angle. Now I should mention, how do you know the wave angle when you're at the beach? Well, you can kind of see the way the water's approaching, but if you are having trouble, you can always look at the wind direction. which direction is the wind blowing? And the winds are always named from where they come from. So we always say winds are named from whence they came. So if you have a west-southwest wind, chances are you're going to have a west-southwest wave direction. So in this case, our wave direction is about 60-degree angle of approach. So that puts us in the red for wave angle. The wave height in this case we'll pretend is 3 feet. So that puts us right in the middle. So we're in that borderline case. But the wave period in this case is 6 seconds. So that's a little bit longer than what we traditionally see. Usually wave period's about 3 to 4 seconds on the Great Lakes. So 5 to 6 seconds gets you into that better chance for water piling up. So what type of currents do you expect with this wave direction? The answer is you can expect the structural current to be pretty strong because we have a 60-degree angle of approach. You have a potential for rip currents given that it's a 60-degree angle, and the wave heights are about 3 feet. And you also have that chance for that strong structural current and longshore current as well. So how do you actually take observations? It's pretty simple. For Silver Beach, this is what your form looks like. We take the observation daily at around 12 p.m. or 3 p.m., depending on when you have the time. And we want you just to estimate the wave heights. You don't have to give an exact number, just like a range, like 3 to 5 feet, 4 to 5 feet. And you assess the rip current activity, the structural current activity near the break wall, and the number of rescues or fatalities you can confirm or strongly suspect were current related. This is the link to the form. And so you see there's the wave height. You can do a drop-down menu, the current activity at the middle stand, and the structural activity along the pier. We also ask for the longshore current strength and direction. And when we say the direction, we mean basically which way is it moving when you're looking out onto the beach. So for example, if you're looking out on the lake and there's no real movement, you would choose not available or unclear because maybe there is no longshore current that day. If the current is moving from left to right, which would basically be from the south-southwest to the northeast, north-northeast, then that's where you're going to say left to right or right to left, which would be pretty unusual given the wave direction usually. So then if you have additional comments you want to add, you can do that as well. So if you had any the state of the surf zone, which is the area where people are swimming, if you want to talk about the waves and their characteristics, perhaps any fatalities or warnings you've given to swimmers, the flag color. If you want to give us a comment about our forecast, that's great. We take them, we read them, we look at them. If you want to talk about cloud cover or lightning, anything you think is important for us to know, especially though those rescues and drownings, we want to see it. And then put your nickname or your code or your number, initials are fine, so we can contact you with questions. And also if there's an issue with the observations, we can kind of correct it if there's a problem. So when you're looking at the wave heights, one of the best ways is to sort of see how high the wave is from the top of the water to the top of the wave. So we say when we want to know the wave height, we want to know how far is it from the surface of the water to the top of that wave. So you can sort of see here, this is the top of the wave. This is a break wall or pier. This is the deeper water below, and then this is where the wave is actually coming up. So what we usually recommend is that you pick a feature or a person that you know the general height of. So pretend our pier is 10 feet high and compare passing waves to that object. So if you know the water's about 4 feet deep here and you know the pier's 10 feet, you can kind of guesstimate that it's about 6-foot wave. And what we say is to try to get the maximum height of the wave before it breaks near the beach. So just as it starts cresting like this, where that white water's coming in, is what you want to be looking at, not so much like the dissipated part when it gets closer to the beach. And another way to do it, and this is something the lifeguards at Silver Beach have found helpful in the past, is to estimate people. So if you know someone's about 6 feet tall, they go into the water and you know the water's about 2 feet deep and you see the wave coming up behind them, you can probably guesstimate it's about 2 to 3 feet given that about 4 feet of the guy is out of the water. So this is an easier way to kind of look at things because you're more often going to be able to tell with people and see how tall they are, and also you can go in and see as long as it's safe to do so. So as far as signs of rip currents and the strength of rip currents, we saw this picture earlier of rip currents at Grand Sable Dunes in Grand Marais, Michigan. And what you're going to see is the sandy water extending perpendicular to the shore or maybe at a little angle to the shore. And then you'll see a break in the incoming waves, such as like right here. If you want to assess the strength, there's several options. If you've had a lot of rescues or reports of strong currents from swimmers, that's usually indicative there's strong currents out there. If you actually go swimming in there and you're doing a rescue maybe or something, you can tell how strong it feels from your personal experience. Is it strong enough to prevent you from returning to shore? Is it, what's the deal? And how far is the sandy water or muddy water extending out in the lake? So in this case, this one's probably a little bit weaker, but this one goes out pretty far. You can see it goes out here pretty good. And it breaks actually through that wave and pushes the water down. So that's probably a stronger one. Here's an example of where the winds were coming in at more of an angle out of the north. So you had that longshore current, but we also had the currents. But notice how they're angled to the beach versus straight out like the last example. And this is the same spot. So you can see those stronger currents here where they're kind of coming out, and even this one in the distance there. Here's another example. You can see the water that's muddy. This is taken from an airplane. This was at Warren Dunes. And you can actually see how wide that is. It's a big offshore flowing water. This is hard to see from the shore, but you can still see that break in the incoming waves. Here's another example. It's a little bit harder to see, but there was actually a current going here. You can see the muddy water. It's a little hard because it was overcast that day. But there was actually a buoy here, and the wave was breaking here. There was a big gap, and then there was another wave here. So there's a break in the waves. There was a current there. And actually those buoy, there's another one off the screen you can't see, but that's actually a current that is well documented and marked with buoys because it's a permanent feature. Here's another example from Indiana Dunes State Park where you can actually see the water going out. That's muddy water, and you can see that break in the waves. And there's another example here. You can't really see the muddy water, but it looks like kind of a calm spot in between the waves. Wells Street Beach. This was posted on their website one morning. They said, oh, it's a nice day to come to the beach. And there was actually, so you could see the rip currents pretty clearly here. If you look at the sandbars on this beach, you can actually look on Google Maps, and it's actually a very dynamic beach where you can see the breaks from the rip currents developing. This is a day with northerly winds, so the winds were coming right on shore at a 90-degree angle, and the waves were about 3 to 4 feet at the time, and they were coming down from about 5 to 6 feet that night. Here's another example. You have a break in the waves right here and right here, and you can't really see muddy water except for right around here. You can sort of see that water going out. Here's another example. This is a structural current. The signs are very similar. You're going to see that sandy or like sort of turbulent looking water heading out. But with the waves crashing, a lot of times it's hard to see. And this is kind of like a jetty that's in the ocean. Again, you assess the strength by seeing how far out it looks to be going, or maybe if you're by the pier and you're standing there looking down in the water, how rapidly it appears to be moving versus normal, and if you have to rescue any swimmers in the current. So those are ways of assessing it. And you can also throw a stick in the water, or some people throw oranges in if you have some fruit you want to throw in and see how fast it's moving. But you know what we are generally looking for, we realize this is subjective. We just want to know, how is it compared to normal from what your experience is. And it will take time. At first you may feel uncertain, but after you observe the current day after day, and the conditions, if you're watching closely, you're going to get a feel for it naturally and an intuition about when it's stronger than it normally is. So an example here, we returned to this picture, we had our rip currents, but if you notice, there's also this calmer area here, and water moving out right along the break wall. And actually, if you look really closely, this was actually a video I screenshotted from an Angel Cam in Holland, Michigan. But what you can't see in this is that when the video was going, the water, you can actually see it moving out, and it was going around and out. And that's that discoloration you see there in those white arrows. Longshore current strength and direction is pretty similar. If you observe the water flowing parallel to shore, if you go out there and you stand in it, is it hard to stand up? Is it stronger than it normally is when you go in? And what direction is it moving when you're facing the lake? Denote whether it's moving from left to right, such as in this picture, or if it's going the other way from right to left. So last but not least, let us know if there's any rescues or fatalities due to currents. The more we know about this, the more we know about when strong currents are present, the more likely we're going to be able to forecast them better in the future. If you have time, and I realize that it's busy because, you know, the number one priority you have is saving lives and getting your procedures taken care of, but maybe later on you have time if the person was rescued Ask them how they got into trouble, if they are able to answer, if they're not too shaken up, if it's not already apparent. Ask them which way the current was pulling them. Was it pulling them along the shore or out in the lake? Was there a current present at all? Include these details in the comment section, and if you get time, ask them their age and where they're from so we can have it for our incident database. The more data we have, the better we're going to have a handle on forecasting, and the more information we have about people that get caught in them, the more we're going to be able to target our outreach and education efforts. So that's the importance of doing this. Before we go on to the end of the presentation, we're going to talk about Severe Weather 101. And this is just generally so that you're aware of what's happening. Key is to observe what's happening around you. What are the clouds doing? And when do you think it's time to come in? And what resources are there for helping you with this? There's 3 stages of a thunderstorm, and generally a thunderstorm cell is about 30 minutes from start to finish. You start with developing cumulus stage, go to the mature cumulus stage, and then you go to the dissipating stage at the very end. So we'll go through these. So you might notice this, that earlier in the day when you come outside on a really hot day and there's not a lot of cloud cover, it's pretty much clear. And what happens is the ground gets really heated up, and as it heats up, it's kind of like an oven burner where you set a pot on it. You know, as the air is an actual fluid, just like water is. And so as that ground heats up, it causes the air nearest the surface to start to heat up. And the heat wants to rise. And so it causes convection, just like it would be a boiling pot. So as the water starts to heat up at the bottom, it gets unstable and it starts to convect. And that's why we call thunderstorms convection. So what'll happen is you'll get an air bubble that rises up, just like a water bubble would, and starts to condense as the air temperature cools. So what will happen is the warm air rises, starts condensing into a cloud. So after a little bit, you'll start to see little cotton balls across the sky. And this is that updraft form, the developing cumulus stage. So it's a cumulus cloud. So usually in this stage, it's just an updraft. There's little to no rain reaching the ground, and there's no severe weather. But usually it lasts about 10 minutes, but it really varies. And sometimes you don't usually even see these for very long, but if it actually gets to the point where we have unstable enough air to create thunderstorms, you'll start to see something taller like this. And notice that the way you can tell it's a really good forming updraft is it looks like cauliflower on the edges. It's very defined, and it's in contrast to what we'll see in a little bit. So once the updraft strengthens enough, eventually it gets so high that instead of just forming clouds, it actually causes a downdraft and rains. So the rain is what precipitates out of the air. As that air keeps rising, you get rain instead. So when you get the rain, that cools the air and it causes a downdraft, and that kind of hits the ground and spreads out, and that's what we call gust front. But this is the mature stage. This is your best chance for lightning, severe weather. So how do you know something's in its mature stage? Well, it's because it's raining, or it looks like it's raining in the distance. You can usually see the rain shaft. You also see it kind of looks like a little anvil as it spreads out, and you're still going to see that thick cauliflower look to it. So you can see here's a great example of the updraft here, and it kind of spreads out as it hits the top of the atmosphere. And you can also see the strong updraft where the cauliflower is. But you can also see here where it's a little bit fuzzy on the edges, and that's where that downdraft is. So eventually what will happen if there's severe weather isn't expected, usually what will happen is the downdraft gets so strong it cuts that updraft off. And this is also a really good period for severe weather, where you have minor wind, heavy rain, lightning. This is your best chance for those more hazardous scenarios. Other storms also could develop along that outflow where that air hits the ground and spreads out. So you might see more storms develop. But one of the things you'll notice is see how the edges are very smooth. And in this picture, they're also very smooth and undefined versus where we had that more cauliflower appearance. So you can see it's really washed out. So that's a signal that that downdraft has cut off the updraft. So this is a cloud you may have seen before, and this is one we see often with thunderstorms on Lake Michigan. This is called a shelf cloud because, well, it looks like a shelf, and it's on the leading edge of a thunderstorm. This usually signals the approach of gusty winds, possible hail, and heavy rain. And in this case, I would argue there's probably some hail because it looks kind of green, and that's something that's caused by the way the light reflects off hailstones. And you can see that it looks kind of smooth and laminar, and that's very typical of a stronger storm. So if you see something like this, a shelf cloud, you're going to want to prepare to get people off the beach. So what's happening in a shelf cloud? And this is a little animation that we have in our spotter training, is that cold air, and it's very dense, drops down out of that updraft and downdraft and hits the ground and spreads out. And that pushes warm air out ahead of it up into which is less dense, up aloft. And it rises and condenses into a cloud, and that forms this shelf-looking feature. So I'll show you again. Air descends and pushes up the air ahead of it, which is moist and less dense, and it starts condensing, and then it forms a cloud. So that's how you get that shelf cloud. This is what it looks like. You can see here, there's the downdraft with the rain shaft, and here it's clear, so there's that warm air out ahead of it. It's less dense, it's rising up, and it kind of is condensing as that cold air comes out from the downdraft. And that's why you notice, like when thunderstorms go through, it gets a little cooler right afterwards because of that down rain cooled air. So as that rain hits the ground, it pushes up the air above it and it goes up. Here's another good example. It looks really well developed. You can see the rain shaft over here in the dark. There's a light out here where we are, and you can see as that air rises up, there's that shelf feature forming again. So another thing that this signals, and this is a big concern for current development specifically, is water level fluctuations. We didn't really talk much about how this impacts current development, but on the ocean, tides such as low tide, like when the water kind of piles up on high tide and then it pulls back out during the afternoon, the low tide period is when it's favorable for current development. And this is because the water is being pulled away from shore already, and the distance between the sandbar top and the top of the water is decreased. So it's sort of like enhancing it, like putting a smaller nozzle on the hose. So while we don't have tides that are significant on the ocean, we do have what's called a seiche, or you may have heard the term meteotsunami. As a strong storm or maybe even a strong front moves across the lake, the water gets pushed to one side. So if you start to see that shelf cloud that forms and you see it kind of coming across the lake, you know that number one, there's going to be winds expected, there's going to be a pickup in the waves, and there's going to be possibility for water level fluctuations, which can enhance the currents. So as that wind comes and blows across the lake, this is the other side of Lake Michigan, it forces water to one side. When the wind stops, it drifts back and forth and it just keeps oscillating. And this can happen for, depending on how strong the storm is, this can happen for hours. And so as that water recedes, people end up getting can get pulled out in those stronger currents. And this actually happened in 2003 along the shoreline of Berrien County when a really strong thunderstorm, I think it was like 60 to 70 mile an hour winds, went through in the morning and pushed all the water up to the side of the beach. And then in the afternoon, when the storm kind of cleared out, the rain stopped. Since it was July 4th, everybody went running outside to go swimming, and those water level fluctuations were still occurring. The wave heights were only about 2 feet at the time. And so what ended up happening, we had 7 people drown in a 5-hour period. This was due to current development. So we want to make sure you're aware of that. So let's pretend you're at the beach and you're the lifeguard on duty. And this is what you observe. What weather would you expect with the passing of this cloud feature? What would happen to possibly the water conditions? And what is this cloud called? So I'll give you a few minutes to think about it. Okay, so hopefully you got an idea. We noticed that it's very calm. So when we see the cloud feature pass, we would expect that, first of all, it's a shelf cloud. As you can see, it looks like a shelf. You can see the downdraft over here in the rain. It's that darker area. So you know that there's warmer air rising up and going aloft above that cooler air, especially with the marine area here. The water tends to cool the air a little bit, and it rises up above that and causes a shelf feature. So you know that when a shelf cloud passes, the winds are going to probably pick up. You're going to see some heavy rain. You might see some hail. So we're also a potential for lightning. That was what we expect weather-wise. But if this storm was strong enough, which in this case it doesn't really look very strong, but if you actually had a stronger one, you might be concerned that the waves are going to pick up to maybe hazardous levels, and that there might be some water level fluctuations for up to an hour or more after. So one of the things we do when we're a little bit worried about severe weather is we'll put out a watch. There's actually a Storm Prediction Center issues a severe thunderstorm watch, perhaps, or a tornado watch. And what that basically is saying is that atmospheric conditions are right for hazardous weather. So this means it's time to prepare to take appropriate action. So when the warning is issued, you can take quick action versus trying to plan it out while you get a warning and the storm's actually on your doorstep. So this is just a time to kind of be aware. So if you come into work and you see that a severe thunderstorm watch is issued for the beach area, you're going to want to be mindful that there could be a potential for some severe storms and also for those water level fluctuations we talked about. A warning means that severe weather is imminent, so you need to get to shelter immediately. So if we issue a tornado warning, that means you need to be taking shelter right away, because it means either a tornado's been spotted by a weather spotter or the public, or perhaps that indicated on radar. So we want people to take shelter immediately. So if you have a severe thunderstorm warning, that is another. You need to make sure people are inside and you need to get to safety. So where can you get this weather info? How do you know if there's a watch out? One of the cool pages we developed recently is called the Weather Watcher page. So it's weather.gov, IWX, Weather Watcher. So this is what it looks like. And this is originally made for emergency managers to use for outdoor events such as fairs or festivals. You'll notice on the tabs it says during the event, day of the event, days leading up to the event, planning and resources. So when you say during the event, it's just basically how do we monitor for what's going on regionally on the radar. So that's going to show you where the storms are. There's a local loop, and it's also going to show you the watches and warnings. So in this case, there wasn't any, but if there were, like a beach hazard statement or something, it would show up on this map as blue, and severe thunderstorm warnings might show up as orange, or tornadoes as red. So there's different warnings that'll show up on this map. You can click on it and read it. This is also the Storm Prediction Center's outlooks. So as you go through the tabs, you can kind of see what things are going on. So the day of the event or the days leading up to the event kind of looks like this, where we have hazardous weather outlooks. So we highlight high swim risk conditions in the hazardous weather outlook and thunderstorms. So there's a lot of relevant things for you guys to look at on this page. We have our weather stories where we do highlight the swim risk and any severe weather potentials. When you go into work in the morning, you kind of have a situational awareness that, hey, today's a day we might have storms, or maybe you look at the weather outlook and you see, oh, in 2 days we might have storms. Maybe we better plan accordingly for that. How are we going to get people to safety if there's an event? So this is just a tool that you can use to just stay aware of the weather and wave situation. So last but not least, if you want to do additional training, because this 1 hour training wasn't enough, you can always do the Dangerous Currents training online module, which has quizzes and things. So if you want to get a better handle on it again, it's a little bit more basic than this one, but it is pretty good. If you want to read more about the incidents and sort of get a feel for or develop an intuition about statistics and the different types of incidents or places that cause currents, you can go to our website and look at the current related incidents. It's an interactive map. So in this case, you highlight Overberrien and that little window right here pops up, and you can actually see how many deaths, how many rescues, how many incidents total there were. You can also read about everything I've taught you here. So if you're more of a reader and you like to digest things, you can go and look at the website. I update it every year, and so what'll happen is in 2018, I'll put up a tab, and you can see each year as it goes along, and I'll say, this is how many incidents we had. Here's where they were. Here's the age of the victims. So it's all that data that we get about the drownings or rescues. And it also has a link to the searchable database if you want to look at certain beaches. You could submit an incident using this form. If it's someone that's not a lifeguard that knows about an incident or something, they can use this form to submit to me directly. And you can also search the database manually. So this is an example of the graphs, and this is just a general overview. At the time, this was 2015, but we just looked at the incidents by year, by lake. A lot of the graphs you saw in here in this presentation are on that website, and if you need more information, you can always reach out to Megan Dodson. And last but certainly not least, if you want to get more of a weather savvy background, we have a lot of really great resources on our Skywarn page. If you go to weather.gov/IWX and you scroll down to the bottom and click Skywarn, You get real-time information, training and reference materials. They give you these like modules and things that you can actually do. So this med-ed spotter training where you can actually learn the details about severe weather and things. You can get handouts, printouts, whatever you want to do, and how to report severe weather. The reporting procedures are different for severe weather than it is for just the currents and things, but it's pretty easy. We just say, give us the time, the event, or the weather, and the location. So that's about it. If you have any questions, feel free to reach out to me at Megan Dodson at NOAA.gov. And you can also text or call me anytime. Just tell me who you are. 586-703-9557 is my cell. Otherwise, you can contact us at the office 24/7, 365 days a year, as we're open all the time because the weather never sleeps. So our number is 574-834-1104. Thanks for taking all the observations. We really appreciate it. And have a great day.